In the past few videos, I've talked about how to calculate voltages and currents for a transformer. In this video, I'm going to summarize these in a few simple equations which would be useful for quick calculations. So these equations are that the primary voltage over the secondary voltage is equal to the number of turns in the primary coil, meaning the number of turns in this coil, divided by the number of turns in the secondary coil, and this in turn is equal to the current in the secondary coil divided by the current in the primary coil. Okay, so we call this the primary coil and that the secondary coil. Secondary coil, primary coil. So let's take a look at quickly review how these equations come about, starting from the first one. We know that, that there's a current in the primary coil. It will produce a magnetic flux, and this magnetic flux will go through the iron core and link to the secondary coil, like this. And when the flux changes, current is induced in the secondary coil. Suppose that this flux is phi. This flux is phi. Now, according to Faraday's law, we know that the induced voltage is equal to minus of the flux change divided by the time taken. And for the flux change, we need to multiply it by the number of turns to get the total flux linkage. Okay. So I can write down this equation for both the primary coil and for the secondary coil. For the primary coil, the V here would be the V primary, the voltage that goes in here. The N would be the number of turns in the primary coil down here. And flux will be the flux produced by the current in the primary coil. Now this flux, as this flux goes round, we would assume that there's no flux leaking out of the iron core. So this would be an ideal case. In reality, some flux would always go out, and we have actually a little bit less of the flux that actually goes through the secondary coil. But for now, I'm just going to assume that all the flux produced by the primary current would go through the secondary coil. So in which case, the secondary coil will experience exactly the same flux as the first coil. So for the secondary coil, I can write down this expression. The corresponding expression for the induced voltage using Faraday's law. For the secondary coil, Ns is the number of turns and Vs is the voltage output. And once we have this, we can just divide the two equations. And you'll find that when you divide the left-hand sides, you get this ratio of the voltages. When you divide the right-hand side, since the flux change and the time intervals are the same, phi and t cancel, and you're left with Np over Ns, and this gives the turns ratio. So in this way, you get the first equation. Now for the second equation, this one or between those two, let's see how they come about. So let me just write down what we need to assume for the second case. We need to assume that we need to assume something actually. We need to assume 100% efficiency. Okay, meaning that the power going into the primary coil, the electric power going into the primary coil, which I'll call, let me call that V in. Let's say V in is the power going into the primary coil, and let's say V out is the power, P out is the power coming out of the primary coil. Now in real life, the power coming out of a device, a real life device like television, computer, electric kettle, would almost always be smaller than the input power, because the power coming out as in the useful power. In this case, the power that actually goes to our house, or in the case of a television, the power that makes the picture for us to see. There will always be some heat which is lost in the electrical wires. So those are wasted power. But assuming 100% efficiency, this means that the output power is equal to the input power, so that there's no heat loss in the device. So making this assumption, we can write down the relation between the voltages and current, because we know that power is equal to VI. We know this formula. VI is the power. So for the input power, the voltages and currents are Vp, the primary voltage, and Ip is the primary current. So it's Vp times Ip. For the output power, we can again use the formula Vi. This time, voltage is the output, is the secondary voltage, Vs. That's Vs. Current is the secondary voltage, which I call Is. And so they are equal. So therefore, I can now rearrange this into this form. So to get the voltage ratio, I can divide both sides by Vs. This gives Vp over Vs is equal to, divide both sides by Ip, you get Is over Ip. And you see that we have now obtained this equation relating the voltage ratio to the current ratio. And the thing to note is this: whereas the ratio for voltages and the ratio for turns number are in the same order, meaning the primary over secondary, the voltage, the ordering for the current ratio is reversed. We have secondary over primary instead of primary over secondary. Okay, the reason is because if we have a bigger voltage, it's because the powers are equal, so that if we have a bigger, say, output voltage, the output current must be smaller, as we have seen in the last example. So using these equations, we can quickly, for example, calculate, say, the currents. If we say the output currents, if we know what the input current is, so just make use of this equation without having to go through this step of using the power formula, or these steps of using the Faraday's law. So let me just put in some numbers just to illustrate an example. this up. Suppose that suppose that the power station generates a voltage of say 1000 volts with its generator, maybe steam engine, boiling water, and all that, and that AC generator here produces a 1000 volts electric power, and this goes into this transformer, in which the voltage is stepped up to, let's say down here is 100,000 volts. 100,000 volts. So this would be the VP, primary voltage, and we want this to be our VS, our secondary voltage. So suppose that we have say 100 turns here. So we have suppose that the primary coil has 100 turns. So that would be the NP. Question is how many turns does the secondary coil have? Right, we want to know the number of turns in the secondary coil. And S, what is it? Okay, and to do this we can use our formula of Vp over Vs equals to Np over Ns. So we know all the numbers here except for Ns. So let me we'll just put in the numbers. So Vp is 1000, Vs 100,000, Np is 100, Ns we need to find. So we have a simple equation here. We can solve for this. Let's cancel the zeros here and here, and then we can rearrange this to give Ns is equal to, that will be 100 times 100, 10,000 turns. So we need lots of turns in the secondary coil. So this is one way that we can use it. Now, suppose that I have this power of 1 megawatt generated by power station, and I want to find the output current. Right, now now that we know the voltage, the output. Now that we know the output voltage, we can actually find the output current by using the power formula, P equals to VI. Okay, but suppose that I just know the current here. Right, suppose that I'm just given the voltage. Suppose that I'm just given the current and the turns ratio. The current and the turns ratio, and I want to find the output currents. Okay, so now let's see. So suppose that we don't know we know that turns ratio is 100. No, wait. Suppose that we know that the secondary coil has 10,000 turns. Suppose that we know this. Okay, and we know that the primary coil has 100 turns. Now, suppose that suppose I don't know the primary and secondary voltage yet. I know the turns ratio. Suppose that I'm given that the input currents, the currents in the primary coil is IP equals to 1000 amperes. Okay, right. So I know the input current, I know the number of turns, and I want to find the output current. I want to find this current that would go into this long cable. Right. So we can use that the one of the earlier equations as well. So this would be NP over NS, the turns ratio, is equal to the current ratio. Now remember that the ordering of the current ratio is reversed to that of the turns ratio and the voltage ratio. So instead of primary over secondary, we would have secondary over primary. And this is what we need to find, and we already know those values. So let's put in the numbers. NP is 100 turns. NS is 10,000 turns. And IS is what I want to find. And IP is 1000 amperes. So we can now solve for IS. Okay, cancel this and cancel those. Therefore IS is 10. IS is 10 amperes. So this allows us a way to find the answer quickly without having to work through the powers and voltages directly.